Alright, so this is 7.3, predicting products of chemical reactions. We've seen a lot about chemical reactions. We've seen how to identify whether or not they're occurring. We now understand how to write a chemical equation. We know how to balance that chemical equation so that we obey the law of conservation of matter. And we know how to include phases to tell the reader exactly what state each one of our products and reactants are in at any time. Now the next challenge is to be able to be given a set of reactants and figure out, okay, if these two things come into contact with one another with enough energy, what products are they going to form? So that's what we're going to try to attack today. And we're going to focus on three real types of chemical reactions. And the first one I want to talk about are combustion reactions, because I think they're the simplest, because their products are, for us, going to be the same always. So a combustion reaction, let's write that word up there, combustion. You probably got that word in your notes from 7.2. All right, now a combustion reaction of a hydrocarbon, let's call it a hydrocarbon, contains just that, a hydrocarbon. So let's put down some propane, C3H8. So that's propane gas, right? Now we're going to add to that some oxygen, because every combustion reaction has to have some oxygen. A little bit of heat to that, so that's what the triangle over the yield sign is talking about. And what we'll find out with the combustion reactions that we study in this class is we are going to have the same two reactants all of the time, okay? And I said this a little bit in section 7.2. I'm just kind of hammering it home even more right now. The same two things every single time in a combustion reaction. Those two things are going to be CO2, gas, and H2O, gas. All right? So now I should be able to give you just the following. We've got the combustion of propane, which is C3H8, it's a gas, and I want you to be able to write the chemical equation for that particular process. You should be able to go ahead and write this full equation. So what does it mean? Well, we're taking the carbons, hydrogen, oxygens, we're rearranging them into a different organization and forming new products, the carbon dioxide and the water. All right, so that's a combustion reaction. Let's look at a second type of reaction then. And let me erase my strokes here. Okay, second type of reaction now, single replacement. So again, single replacement reactions we should be pretty familiar with, because our last lab highlighted a lot of single replacement reactions. And so I'm going to use iron again, because iron's a pretty common thing in single replacement reactions. We use it quite often. But this time I'm not going to work with copper. I'm going to work with, let's go with silver phosphate. Silver phosphate. And we want to see if a reaction is going to occur. Now, what we need to identify is which metal is stronger. Is the iron stronger, or is the silver stronger? In our chemical lab that we did between copper chloride, copper 2 chloride, and iron, we found out that iron was stronger than copper, because iron kicked copper out of the bond and then went to bond with chlorine. So in this case, we are going to try to investigate that again. Is iron stronger than Ag, than the silver? And if it is, we're going to get a chemical reaction to occur. So we're going to get the iron to actually combine with the phosphate. And we're going to get FePO4. So let's say we produce iron 3 phosphate. The silver then gets kicked out, right? So we get the silver that's left over. And that's the single replacement reaction. All right, now we'd have to balance this thing, and I'm sure you could do that. You're all intelligent balancers. What do we need? A 3 there, and we're good? All right, excellent. Obviously, the phases are important. We'd have to stick those in there, but for brevity's sake, I'm just going to skip out on most of our phases for right now for single replacement reactions. Maybe I'll highlight them. Okay, silver, we got a solid. Iron phosphate, aqueous. This stuff, aqueous. That's solution. Now, it isn't just metals that get to partake in the single replacement reaction. Nonmetals can do this as well. So let's say I've got something that's pretty reactive, like fluorine gas. And I'm going to put next to that fluorine gas a little bit of sodium chloride, NaCl. And that's going to be solid. And I want to know if a reaction is going to occur. Now, the fluorine is a nonmetal. The chlorine is the other nonmetal. So it would be those two entities, the fluorine and the chlorine, that actually do the exchanging in this particular process. So we're going to get the sodium to break its bond with the chlorine atoms and to now form a new bond with the fluorine to form NaF. That's going to be our new solid. On the other hand, the chlorine gets kicked out. So the chlorine is just Cl2. Got to remember the 2 because it is diatomic, right? It's diatomic. Okay? So that is our equation. So we can have two types of single replacement reactions. One type replaces metal atoms. The other type replaces non-metal atoms. Okay, so we have combustion reactions and single replacement reactions. Now the third type of predictability reactions, predictable reactions. Maybe that's a better word. Let's call these, and we've discussed them already, obviously double replacement. A couple of different terms for these: double displacement, double replacement. They all mean the same thing. All right, let's take sodium sulfate, Na2SO4, and that's going to be aqueous. And we want to add that to, let's see, a solution of potassium. Nah, potassium is not a good one. How about calcium? How about calcium chloride? CaCl2, right? That's aqueous. Now, we want to see if this reaction is going to occur. Now, here's a little trick, a little hint, everybody. Not all of these reactions, not all of these combinations will actually result in a chemical reaction. Sometimes when you put two things together, nothing at all happens. Okay? So we need to have some type of device that tells us, well, when does a reaction occur and when doesn't a reaction occur. So let's just take a look at this for a second. Let's assume that this reaction does in fact occur. So the calciums and the sodium switch. So we then get calcium sulfate, CaSO4, and I'm going to leave out the phases for now. And the other thing that we get is sodium chloride, NaCl, and I'll worry about balancing in a second. Okay, now I have to be able to figure out if this reaction is going to occur. So you are all going to get a sheet in class tomorrow that is going to help you out. It is called a solubility sheet. In order for a double displacement reaction to occur, you need to have a solid form. Okay, you need to have a solid form. So you remember the test tube that we had in class with the white solid that formed on the bottom of the test tube during our types of reactions activity. That white solid must be present in order for these reactions to occur. So here's what this chart is going to look like that you get. Yeah, I know, there's a lot of stuff there. And we are going to have to find both of our products. So the first product that we had was sodium chloride. So let's find sodium chloride and let's go intersect them right here and right there. And boom, when we do that, we get this. We get an S. So let's figure out what that means. S means soluble. Soluble means that it will dissolve in water. So that means that our NaCl, and I'll go back to the other page in a second, is aqueous. It is not a solid. Oh boy. All right, so we're done with that one. Let's look at our other one now. We had calcium sulfate as the other one. So there's calcium. Where's sulfate? Here's sulfate. All right, let's go find them. SS. SS. SS means slightly soluble. Guess what, guys? That means soluble as far as we're concerned. Okay? That totally means soluble. So, for our purposes, I'm trying to get back to that page that I had. I don't think I'm going to be able to. Let's go to this guy. So for our purposes, when we have NaCl, aqueous, plus calcium sulfate, those are our two. Let me go back here, guys. So let's see. We started out with sodium sulfate. That's better. Plus CaCl2. And we formed CaSO4 plus NaCl. What did we find? We found that both of the products were aqueous. So in our case, if we find that, if that's AQ and that's AQ and the stuff on the right is AQ and this is AQ, then guess what? We don't have a reaction. So this actually doesn't occur. So if you look at that table and you see that both of the products are soluble or slightly soluble, you don't even have to write the products down. You don't have to balance. You don't have to worry about phases. You just write NR for no reaction. Okay? Kind of makes life simple. On the other hand, if you do go to that table, and let's just pick something out that does happen to be insoluble. Say one of the products that you formed was iron carbonate. Okay, iron carbonate. So let's say that it was iron 2 carbonate. So you had FeCO3. That would be insoluble. So you put an S down for a subscript. And oh my goodness, is that confusing, because we have S's here, and they mean exactly the opposite of the S right here. The S right there means soluble in water. The S right there means it's a solid. So you have to keep those things straight, I understand. If you don't want to use an S down here for a subscript, you could also use the other term, PPT. PPT means precipitate. And actually that's the definition of that solid. So a solid, well, let's just write that down, precipitate. No, not this, not when it rains, okay, or snows. Precipitate is the solid that forms from a double replacement reaction, from a DR, or double replacement reaction. Okay, that's the precipitate. So here's your test tube right there, and you've got some water inside of that test tube, and not water, but two different solutions, and you get that precipitate to form on the bottom. That is the precipitate. Okay, that's the precipitate. Now, I want to take this one step forward further, and I want to show you the different types of ways that we can write these double replacement reactions. So again, I'm going to go with, let's see, two different things. Let's go iron chloride, which is aqueous, plus, let's see, sodium carbonate, Na2CO3, which is also aqueous. Okay, when this reaction occurs, you get, and I'll balance it right away, sodium chloride, which is aqueous, and then you get solid iron carbonate, FeCO3, which is a solid. Okay, so we really want to know what's going on the particle level for this particular reaction. So if I could look inside of my beaker and fill that beaker up with some water, and I want to put in the iron chloride and the sodium carbonate. What's going to happen is this material, the iron carbonate, is going to form on the bottom. So the iron will stick to the carbonate ion, and you're going to get FeCO3 that sticks to the bottom of your beaker. What does it mean to be aqueous then? So what does it mean to be NaCl aqueous? That means that the Na and the Cl are actually not combined with each other. They're electrolytes. So they get to float around in solution as ions. So you've got an Na plus, a Cl minus, a Cl minus, and Na plus. And they're in the exact 1-to-1 ratio that they are in the formula. Okay? But they're torn apart from each other. That's why they're not in the crystalline form, and that's why we can't see them in the solution. They're dissolved in the water. All right, so what that's going to be able to help us just kind of realize the type of reaction that's going on with the double replacement reaction. When you have that solid formed on the bottom, that's your precipitate. Your other aqueous material is going to be located inside of the beaker in its ion form, where you have a cation that's positive and an anion that's negative, and that are separated from one another. All right? That's 7.3.